Space is not loud. It does not roar. It does not echo. It does not warn you when something goes wrong. It is silent, completely, eternally silent. Now imagine floating just outside a spacecraft. The curve of Earth glowing beneath you. The vast black ocean of space stretching infinitely in every direction. You are tethered, safe, trained, in control, until suddenly you're not. A small malfunction, a broken tether, a burst of gas from a maneuvering unit, and in a matter of seconds, the distance between you and safety begins to grow. Slowly at first, then inevitably. No sound, no dramatic explosion, just motion and nothing to push against. You reach for anything, a handrail, a line, a tool. But in space, there is no friction, no air resistance, no natural way to stop yourself. Newton's laws take over. Every tiny force becomes permanent motion, and the spacecraft that once filled your vision begins shrinking into the darkness. How long would you survive? Would you freeze instantly? Would you explode from the vacuum? Could you be rescued? Or would you simply drift, orbiting Earth forever? A silent satellite made of flesh and metal? Tonight, we explore what really happens if an astronaut drifts away in space, not through drama, but through physics, biology, and the unforgiving mechanics of the universe. Before we imagine the worst-case scenario, we need to understand the environment itself. Space is not just empty. It is a near-perfect vacuum, meaning there is almost no air, no pressure, and no medium to carry sound or heat in the way we experience on Earth. Contrary to popular belief, a human body does not instantly explode in space, nor does it freeze solid in seconds. The reality is more complex and more unsettling. Without atmospheric pressure, gases inside the body expand. Oxygen in the bloodstream rapidly depletes, and consciousness begins slipping away faster than most people realize. But survival is not just about biology. It is also about physics. In orbit, everything is constantly falling around Earth at incredible speeds, roughly 28,000 kilometers per hour aboard the International Space Station. If an astronaut drifts away, they are not floating aimlessly. They are still moving at orbital velocity. That means rescue is not as simple as flying toward them. Matching speed, trajectory, and momentum becomes a delicate and time-sensitive calculation. Even a difference of a few meters per second can separate life from death in the vacuum of space. So what truly happens in the first seconds? The first minute? The final moments? And is there any realistic chance of survival? To answer that, we must break the scenario down step by step, combining real astronaut training protocols, human physiology, and the cold precision of orbital mechanics. Now, let's begin at the moment the tether snaps. It begins with something small, not an explosion, not a dramatic alarm, just a subtle shift in tension. The tether that connects you to the spacecraft loosens for a fraction of a second, then snaps free. For an instant, nothing feels different. Your body is already weightless. You are already floating, but then you notice the station drifting away, slowly, silently. There is no sound in space to announce the mistake. No wind rushing past your helmet, only motion. Your training activates immediately. Do not panic. Assess velocity. Stabilize rotation. You fire a small burst from your maneuvering unit, attempting to counter the drift. But in orbit, even the smallest force matters. If the initial push that separated you created even a slight difference in velocity, just a few centimeters per second, that difference now compounds with every passing moment. The spacecraft grows smaller. Earth rotates beneath you in majestic indifference. Your visor reflects blue oceans and white cloud systems, beautiful and unreachable. You check your oxygen levels. You have limited supply, but enough for a spacewalk. The problem is not immediate suffocation. The problem is distance. At orbital speed, both you and the station are traveling at nearly 28,000 kilometers per hour around Earth. You are not falling downward. You are falling sideways, perpetually missing the planet. And unless your trajectory perfectly matches the station's orbit, separation becomes inevitable. You attempt another controlled burst. Too much thrust could send you spinning. Too little does nothing. Your body rotates slowly now, stars replacing Earth in your field of vision. Instinct screams for something to grab, but there is nothing. No friction, no resistance. Newton's first law dominates this moment. An object in motion stays in motion unless acted upon by an external force. And there is no external force out here. Inside the suit, your breathing accelerates. Carbon dioxide begins rising slightly. The suit's systems compensate, but stress increases metabolic demand. Every breath consumes precious oxygen. Mission Control is speaking in your ear now, calm, precise, calculating. They are tracking relative motion, computing vectors, estimating drift rate. The question becomes brutally simple. Can the station maneuver toward you faster than orbital mechanics separates you? Even a separation rate of 1 meter per second becomes 60 meters after 1 minute, 300 meters after 5 minutes. Distance in space grows quietly but relentlessly. You attempt to orient yourself toward the station, minimizing tumble. Rotational drift is dangerous. Spinning disorients you and complicates rescue calculations. You extend your arms instinctively, as if swimming through water, but there is no water to push against. Movement without propulsion changes nothing. The psychological weight begins pressing harder than gravity ever did. The station is still visible, a structured, mechanical symbol of safety, but it is shrinking. Sunlight reflects sharply off its panels, briefly blinding. Then you drift partially into Earth's shadow. Temperature begins to drop. In direct sunlight, your suit can heat rapidly. In shadow, it cools just as quickly. Space is not uniformly freezing. It is thermally extreme. Your suit regulates internal temperature, but external surfaces fluctuate drastically. Meanwhile, the physics continues. If your orbit differs even slightly in altitude from the station's, you may begin drifting above or below its path. Orbital mechanics are counterintuitive. To catch up to something ahead of you, you often must drop into a slightly lower orbit to increase speed. But you have limited propulsion. Every decision matters. Mission Control calculates whether a rescue maneuver is feasible. Fuel margins are tight. Time is narrower. Inside your bloodstream, oxygen saturation begins its slow decline. Not dangerous yet, but measurable. If pressure were lost, unconsciousness would occur in roughly 15 seconds. But your suit remains intact. This is not decompression. This is isolation. The most terrifying realization arrives quietly. You are not falling away from Earth. You are becoming your own satellite, a human-made object in stable orbit. If rescue fails, you will circle the planet endlessly until oxygen runs out. Your visor fogs slightly as breathing intensifies. You consciously slow it down. Inhale, exhale, conserve. The station is now hundreds of meters away, still close in cosmic terms, infinitely far in human terms. Mission Control informs you they are evaluating maneuver options. The commander prepares to use limited thrusters. Fuel calculations scroll across screens in Houston. They must match not just your position, but your velocity vector in three-dimensional space. A rescue approach too fast could push you further away. Too slow, and time expires. The sun rises again over the curve of Earth, flooding your suit in white brilliance. For a moment, the planet looks peaceful. Storm systems swirl over oceans. Continents drift beneath you. Humanity lives unaware of the fragile human form orbiting above. Inside your helmet, heart rate spikes. Training says focus on numbers. Oxygen remaining. Distance rate. Orientation. But another thought intrudes. If rescue fails, there will be no impact, no explosion, no dramatic ending. Just gradual hypoxia, vision narrowing, consciousness fading, and then eternal orbit. The station fires its thrusters. You see a subtle flash. It begins adjusting trajectory. Hope exists, but physics decides the outcome. Every second stretches longer than the last. You are suspended between mathematics and mortality, and the universe remains completely silent. Inside the suit, everything still feels controlled, but the clock has already started ticking in ways that are invisible to the naked eye. Your oxygen supply is stable for now, circulating through the life support system, maintaining pressure close to what your body needs to function. The suit is your artificial atmosphere, your only barrier between biology and vacuum. If it remains intact, survival becomes a question of oxygen duration and rescue timing. But if that barrier fails, even partially, the timeline becomes brutally short. In a near-perfect vacuum, atmospheric pressure drops to almost zero. Human lungs are adapted to operate at Earth's surface pressure, where air pushes gently against tissue. In space, that pressure disappears instantly. If a helmet were removed or the suit ruptured, the air in your lungs would expand rapidly. This is why astronauts are trained never to hold their breath in decompression scenarios. Expanding air can rupture delicate lung tissue in seconds. Assuming air escapes safely, the next stage is hypoxia. Without oxygen entering the bloodstream, brain cells begin suffering almost immediately. Within 10 seconds, vision starts dimming. Peripheral sight narrows. Cognitive function declines. At roughly 15 seconds, unconsciousness occurs. There is no dramatic explosion of the body. Skin is elastic. Tissues are strong. You would not burst apart. Instead, a phenomenon called ebullition would occur. Because body temperature is higher than the boiling point of water in a vacuum, moisture in exposed tissues begins to vaporize. Saliva would bubble. Tears would evaporate. The tongue and eyes would swell. The body would expand slightly, perhaps doubling in visible size. But structural tissues prevent catastrophic rupture. Meanwhile, internal organs remain largely intact, though deprived of oxygen. Brain damage begins around 2 minutes without oxygen supply. Beyond that, recovery becomes unlikely. But in your case, the suit is still sealed. Pressure is stable. Oxygen is flowing. That means the threat is slower, more psychological, and just as lethal. As stress rises, breathing rate increases. Increased respiration means increased oxygen consumption. Carbon dioxide levels inside the suit begin climbing faster than normal. CO2 buildup is dangerous. Even small increases cause headaches, confusion, and panic. The suit scrubbers work continuously to remove carbon dioxide, but they are designed for controlled breathing, not sustained panic. Your body responds to fear with adrenaline. Heart rate accelerates. Muscles tense. Energy consumption spikes. Ironically, the more you panic, the faster your life support drains. Temperature regulation becomes another factor. In direct sunlight, external suit temperatures can exceed 120 degrees Celsius. In shadow, they can drop below -100. However, because space lacks air, heat transfer is not immediate. There is no convective cooling or heating. Temperature changes occur through radiation. The suit's thermal control system circulates liquid cooling to maintain internal stability. Without it, overheating could occur within minutes during sun exposure. Dehydration also begins subtly. The suit contains limited water supply. Stress increases fluid loss through respiration and perspiration. Dry mouth intensifies. Swallowing becomes uncomfortable. You attempt to remain calm, but the human brain is not built for infinite emptiness. The absence of sound removes one of the most fundamental sensory anchors. No wind, no vibration, only the faint hum of life support fans inside your helmet. Your inner ear struggles with orientation. Without gravity as reference, even small rotations can create disorientation. Nausea threatens. Space adaptation syndrome, similar to motion sickness, may reappear under stress. Meanwhile, mission control continues calculations. Every passing minute reduces rescue probability if distance increases. From a biological standpoint, the critical threshold is oxygen reserve. Most extravehicular mobility units provide roughly 6 to 8 hours of life support under normal usage. But emergency reserves are not designed for extended, uncontrolled drift. Power systems also matter. Batteries run communication, telemetry, heating, and CO2 scrubbing. Once power fails, oxygen circulation stops, temperature regulation collapses, and carbon dioxide accumulates rapidly. Hypoxia under gradual oxygen depletion feels different from sudden vacuum exposure. Instead of instant unconsciousness, symptoms progress. Mild headache, slowed thinking, tunnel vision, muscle weakness, judgment impairment. Ironically, as oxygen levels drop, awareness of danger decreases. Victims often feel euphoria or calm before losing consciousness. It is a silent shutdown. If rescue remains possible within the oxygen window, survival chances remain high. Human bodies can recover fully from brief hypoxic episodes if oxygen is restored in time. But beyond several minutes without oxygen flow, neuronal damage becomes irreversible. Radiation exposure is another long-term factor. Earth's magnetosphere protects low-orbit astronauts from the worst cosmic radiation, but extended time increases exposure risk. Solar flares pose acute danger, though unlikely in such a short scenario. Still, without spacecraft shielding, your suit offers limited protection. Through it all, the most immediate biological enemy is not vacuum, not freezing, not explosion. It is oxygen depletion combined with psychological stress. The body is remarkably resilient in short-term vacuum exposure. The mind, however, struggles under isolation. Cortisol levels rise. Decision-making narrows. The brain seeks control in a situation governed by physics. You try to regulate breathing. Inhale slowly. Exhale slowly. Lower heart rate. Conserve oxygen. The suit displays remaining time. Numbers tick downward with indifferent precision. You are physically intact. You are not freezing instantly. You are not exploding. You are surviving temporarily. But survival in space is not about strength. It is about time, trajectory, and systems functioning perfectly. Biology can endure more than most imagine, but it cannot endure indefinitely. And the oxygen counter continues its silent countdown as you orbit the Earth alone. Rescue in space is not a matter of simply flying towards someone and pulling them back. It is a problem of velocity, vectors, fuel margins, and unforgiving orbital mathematics. At the altitude of the International Space Station, both the station and the drifting astronaut are traveling around Earth at roughly 7.66 kilometers per second. That speed is not optional. It is what keeps them in orbit. They are constantly falling toward Earth, but their sideways velocity causes them to miss the planet again and again. When the tether snapped, the astronaut did not suddenly slow down. They retained almost the exact orbital velocity of the station. The danger comes from tiny differences. Even a push equal to the force of a gentle shove on Earth can translate into a measurable divergence in orbit. If the astronaut drifts slightly higher than the station's altitude, their orbital speed decreases. Higher orbits move slower. That means the station would gradually move ahead. If the astronaut drifts lower, their orbital speed increases, and they may begin pulling ahead of the station. This counterintuitive behavior confuses many people. In orbit, to catch up to something ahead of you, you often must first drop lower to move faster, then rise back up at precisely the right moment. That requires fuel, and fuel aboard a spacecraft is one of the most precious resources available. The station itself has limited propulsion capability. It can adjust its orbit gradually, but aggressive maneuvers are costly. Mission control must calculate whether the station can safely alter its trajectory without compromising structural safety or future mission plans. Meanwhile, the astronaut may have a small simplified aid for EVA rescue system, known as SAFER, essentially a miniature jetpack designed for emergencies. It carries limited nitrogen gas propellant. Under ideal conditions, SAFER allows an astronaut to counter small drifts and return to the airlock. But its fuel supply is extremely limited, designed for short corrections, not large-scale retrieval missions. Every burst must be controlled. Overcorrecting could send the astronaut into a spin. Spinning introduces angular momentum, making precise navigation harder. If the astronaut begins tumbling, they must first stabilize rotation before translating toward the station. Stabilization itself consumes fuel. From mission control's perspective, the problem becomes one of relative motion. Radar and tracking systems measure separation distance and velocity vectors. Computers simulate intercept trajectories. But unlike docking two spacecraft with ample propulsion, here one object has minimal maneuvering capacity. Timing becomes critical. The longer the delay, the greater the separation. Even a steady drift of half a meter per second results in 30 meters after 1 minute, 180 meters after 6 minutes, and over a kilometer after half an hour. In the vacuum of space, a kilometer is nearly impossible to traverse without propulsion. If the astronaut's drift vector aligns such that they are moving slightly outward from Earth, they may enter a higher elliptical orbit. The station, remaining in its original path, would gradually fall behind. Alternatively, if the astronaut drifts inward, atmospheric drag at slightly lower altitudes could subtly alter their trajectory over time, though not quickly enough to help in the short term. There is also the question of line of sight. As both continue orbiting Earth, planetary curvature may block visual contact. The station could pass into darkness, while the astronaut remains in sunlight. Relative orientation shifts constantly at orbital speed. Communication remains active, but visual cues diminish. Rescue requires precise burns. If the station fires thrusters to adjust orbit, it must account for Newton's third law. Every action has equal and opposite reaction. Thruster firings slightly jolt the structure. Crew inside brace for microaccelerations. Calculations must consider orbital mechanics in 3 dimensions, including Earth's gravitational variations and minor perturbations. Unlike cinematic portrayals, there is no room for reckless heroics. A mistimed maneuver could waste fuel and eliminate any future rescue opportunity. The astronaut, meanwhile, must maintain composure. They may attempt small, safer bursts to reduce relative drift, but each pulse changes velocity permanently unless countered. Orbital motion is unforgiving. There is no air resistance to slow mistakes. Everything persists. If the astronaut's velocity relative to the station becomes too great, intercept may be impossible within fuel constraints. In that case, the grim reality emerges. The astronaut becomes an independent orbiting object. Eventually, atmospheric drag at low Earth orbit would cause gradual orbital decay over months or years. The body would re-enter Earth's atmosphere and burn up like space debris. But that is a distant outcome. In the immediate time frame, the focus remains oxygen and fuel. There are scenarios where rescue succeeds. If separation is small and vectors align favorably, the astronaut can null relative velocity and gently thrust back toward the station. Mission control would guide every movement: pulse duration, orientation angle, stabilization timing. The final approach must be slow, measured in centimeters per second. Too fast, and collision risk increases. Space docking procedures demand extreme precision. The physics allows survival, but only within tight margins. Space is not actively hostile. It does not chase or strike, but it offers no forgiveness for error. Every gram of propellant, every decimal of velocity, every second of reaction time shapes the outcome. In orbit, survival is not determined by strength or willpower. It is determined by mathematics. And mathematics, unlike emotion, does not negotiate. Long before oxygen runs out, long before fuel calculations reach zero, another battle begins. One that takes place entirely inside the mind. Humans evolved under open skies, surrounded by sound, atmosphere, gravity, and other living beings. Even in isolation on Earth, there is wind, distant noise, subtle vibrations through the ground. In orbit, drifting alone, there is none of that. The silence is not peaceful. It is absolute. Inside the helmet, the only audible presence is the low mechanical hum of circulation fans and your own breathing, amplified unnaturally by the confined space. Each inhale sounds louder than it should. Each exhale feels heavy. The awareness that nothing exists between you and infinite vacuum presses against your thoughts. The spacecraft, once a structure of safety and companionship, is now a distant object shrinking against the curvature of Earth. The brain begins searching for control, replaying the moment the tether snapped. Could it have been prevented? Was there a warning? Did you miss a signal? Regret forms quickly in high-stress situations, even when events unfold beyond reasonable reaction time. Training instructs astronauts to compartmentalize emotion, to focus on procedure. But cognition under extreme isolation behaves differently. The human nervous system is wired for connection. Eye contact, touch, proximity, these are stabilizing forces. Now there is only distance. As separation increases, perception of scale becomes distorted. Earth appears close, almost reachable, yet it is hundreds of kilometers below. The station appears small, yet it represents survival. Without atmospheric haze, space provides no depth cues. Everything looks deceptively near and impossibly far at the same time. Time perception begins to warp as well. Seconds feel stretched. Mission control speaks calmly through the headset, but the delay between responses feels longer than it truly is. The brain under stress exaggerates silence between words. Heartbeat becomes noticeable inside the suit. You feel your pulse in your neck, in your temples. Cortisol and adrenaline flood the bloodstream. Vision sharpens briefly, then begins to narrow. Not from hypoxia yet, but from psychological overload. Panic is the greatest threat to survival. Panic accelerates breathing. Accelerated breathing increases carbon dioxide. Elevated CO2 levels intensify feelings of suffocation, even when oxygen remains adequate. It becomes a feedback loop. Astronaut training emphasizes controlled respiration, precisely because the mind can become the primary enemy. You attempt to anchor yourself visually to Earth. Continents rotate beneath you in majestic indifference. Storm systems swirl with silent violence. Cities glow faintly along coastlines. Somewhere down there, billions of people move through ordinary lives, unaware of the fragile human form circling above. That contrast amplifies isolation. You are both incredibly close to humanity and completely unreachable. The psychological phenomenon known as the overview effect, often described by astronauts as profound when viewing Earth from space, shifts tone under crisis. Instead of wonder, the view becomes bittersweet, beautiful but inaccessible. Communication remains your last tether to connection. Voices in your ear remind you that you are not entirely alone. Yet the physical absence of another human body nearby creates a unique strain. Studies in extreme isolation environments, such as Antarctic research stations and underwater habitats, show that prolonged separation can distort cognition, emotional regulation, and decision-making. In space, those effects compress into minutes. The knowledge that survival depends on precise calmness adds pressure. You must think clearly, but fear intrudes uninvited. The mind imagines worst-case outcomes automatically. What if rescue fails? What if propulsion misfires? What if oxygen drains faster than expected? These thoughts arise spontaneously. Training provides mental scripts to counter them. Focus on measurable data. Repeat procedures, control breath, trust the team. But underlying it all is a deeper existential realization. You are a biological organism floating in an environment that was never meant for life. The universe does not oppose you. It simply does not notice you. That indifference can feel overwhelming. At some point, acceptance may begin replacing panic. The brain cannot sustain peak fear indefinitely. It either regains composure or transitions toward emotional shutdown. Some individuals under extreme threat report a strange calm, a narrowing of awareness to immediate sensory inputs. Breathing. Numbers on the display. The slow rotation of Earth beneath. This state can be beneficial, conserving oxygen and mental energy. But if oxygen levels begin to fall, cognitive impairment creeps in subtly. Mild confusion, slowed reaction times, a sense of detachment from reality. Hypoxia does not announce itself dramatically. It gently dims the edges of consciousness. In isolation, without external reference, that dimming can go unnoticed. The greatest psychological challenge is not screaming terror. It is quiet fading, the possibility that awareness might slip away unnoticed while still orbiting the planet. Yet human resilience is extraordinary. Astronauts undergo intense psychological screening and training specifically to withstand extreme scenarios. Visualization exercises, emergency drills, stress exposure simulations, all designed to prepare for moments like this. Whether rescue succeeds or fails, the mind must endure until the final outcome is determined. In the vastness of space, courage is not loud. It is measured in controlled breaths and steady hands. And as Earth continues its silent rotation below, the greatest struggle unfolds not against gravity, but against the fragile limits of human consciousness. At this stage, the outcome balances on margins so small they are measured in decimals. Distance, velocity, oxygen remaining, fuel available. The universe does not lean toward mercy or tragedy. It simply follows equations. If the station's thrusters have adjusted trajectory with enough precision, if relative velocity has been reduced to near zero, if the astronaut has conserved enough propellant to stabilize and align, then a narrow corridor of survival opens. The station inches closer, not dramatically, but gradually, measured in centimeters per second. In orbit, slow is safe. Too fast, and momentum becomes deadly. The astronaut fires a final controlled burst from the safer unit, canceling a slight lateral drift. The station's robotic arm may extend, or another crew member may secure themselves at the airlock, anchored, waiting. As distance closes to tens of meters, visual clarity returns. The structure grows from a shrinking speck into a recognizable machine of survival. Earth continues rotating beneath, indifferent to the tiny drama unfolding above it. The final approach demands absolute stillness. Relative motion must be almost non-existent. A hand reaches out. A tether is thrown. Contact. The moment fingers close around solid structure again, physics shifts from abstraction to relief. The astronaut is pulled slowly inward, careful not to introduce new momentum. Airlock repressurization becomes the most beautiful sound imaginable. The hiss of atmosphere returning. Inside, gravity has not returned, but safety has. Oxygen flows freely. The helmet comes off. The ordeal ends not with explosion, but with breath. Rescue in orbit is possible, and history shows that emergency propulsion systems have been tested and proven effective within limited ranges. Survival, in this branch of possibility, becomes a testament to preparation, engineering, and the quiet precision of mathematics working in humanity's favor. But there is another branch. If fuel margins prove insufficient, if separation grows beyond maneuvering capacity, if timing slips just slightly outside feasibility, then the astronaut transitions from crew member to independent satellite. The station becomes a distant shape, then a point of reflected light, then invisible against the starfield. Communication may persist for a time, but signal strength weakens with distance and orbital geometry. Oxygen counters continue their descent. There is no violent end, no cinematic detonation. Inside the suit, systems continue functioning exactly as designed. The body remains intact. The mind drifts between clarity and fatigue. As oxygen levels decline, symptoms advance predictably. Increased breathing effort, subtle dizziness, narrowing vision. Thoughts become slower, less structured. The sense of urgency fades, replaced by an odd calm as hypoxia deepens. Eventually, consciousness slips quietly away. The heart continues briefly, then stops as oxygen deprivation becomes complete. The body remains sealed within the suit, orbiting Earth along a path defined by initial conditions. Over time, atmospheric drag at low Earth orbit exerts its nearly imperceptible influence. At altitudes around 400 kilometers, trace atmospheric particles still exist. They create drag measured in microscopic forces, but over months and years, those forces reduce orbital energy. The orbit decays gradually. The astronaut's path spirals inward almost invisibly. Eventually, re-entry occurs. Friction with thicker atmosphere generates immense heat. Most objects in low Earth orbit burn up during this phase. The suit, the body, the remaining hardware would likely disintegrate into plasma, streaking briefly across the sky, indistinguishable from natural meteors. From the ground, if visible at all, it would appear as a fleeting line of light. The universe would close the equation without ceremony. Yet there is also a third, rarer scenario. If orbital parameters shift outward instead of inward, if the astronaut drifts into a slightly higher stable orbit and atmospheric drag becomes negligible, the body could remain aloft for decades. A silent human satellite circling Earth thousands of times, witnessing sunrises and sunsets every 90 minutes, forever beyond reach. Over long timescales, gravitational perturbations from the Moon and Earth's uneven mass distribution would slowly alter the orbit. But the process would be measured in years, not moments. The astronaut would become part of the artificial ring of debris humanity has already placed around its planet. In all outcomes, the core truth remains the same. Space does not actively destroy. It simply allows physics to unfold without resistance. On Earth, air slows falling objects. Water cushions impact. Friction corrects motion. In orbit, there is no correction. Every action persists. Every velocity endures. Survival depends entirely on preparation and immediate response. The image of an astronaut drifting helplessly into darkness is powerful because it confronts us with our fragility against infinite scale. Yet it also highlights something remarkable. Humans have built machines capable of sustaining life in an environment fundamentally hostile to biology. We have learned the equations well enough to walk outside our planet and return safely. Most spacewalks end exactly as planned, with re-entry into the airlock, removal of the suit, and continuation of exploration. The drifting scenario is rare, statistically unlikely, and mitigated by redundant safety systems. But possibility alone forces us to confront reality. In orbit, there is no drama added by sound or wind or explosion. There is only silence and motion. If rescue succeeds, it is not because the universe intervened, but because preparation aligned perfectly with physics. If rescue fails, it is not because space is cruel, but because mathematics remain consistent. And perhaps that is the most humbling realization of all. The universe does not choose outcomes. It simply calculates them. Whether pulled back into the airlock or left to orbit alone, the astronaut's fate is written not in emotion, but in velocity, oxygen, and time.